Hello, Mr. Long. So for part A, we know that the bob has a gravitational force of F of G pointing downwards and has a tension force pointing in this direction. And now for part B, using the data in the table, we need to graph a straight line whose slope can be used to calculate the numerical value for G. Alright, so to get a straight line, we know that y is equal to mx plus b. That's our basic equation. So using the data in the table, we can set up our period for a simple pendulum, since this is a simple pendulum. So that's going to be t is equal to 2 pi times radical L over G. And to get it in this form, we can square both sides. So that leaves us with t squared is equal to parentheses 2 pi squared times L over G. And since the pi parentheses 2 pi squared over G is just a constant, that's going to be our m. Which means that our t squared is going to be our y. And our x is going to be L. So our vertical axis is going to be t squared. And our horizontal axis is going to be L. So now we go ahead and put that into our data table. So this is going to be t for period in seconds. And it's going to be t squared for second squared. Alright. Now, I already did all the equations in on my calculator just to save time. And I did it by dividing the time for 20 oscillations by 20 to get our period. And then to get our t squared, I just squared those values. So for the first one, for the length of pendulum at 0.2, I got 0.9, and t squared is going to be 0.81. And then I just went ahead and did them for all of them. So this is going to be 1.096. T squared is going to be 1.2. This one is going to be 1.27. And this is going to be 1.613. This is going to be 1.41. And this is going to be 2. This is going to be 1.56. And this is going to be 2.42. And the last one is going to be 1.69. And this is going to be 2.856. And then going back over here, so that we could calculate the numerical value of acceleration g, we could just go ahead and multiply g on both sides right here, which gives us g times t squared is equal to parentheses 2 pi squared times L. And then we go ahead and divide t squared on both sides, which gives us g is equal to parentheses 2 pi squared times L over t squared. So that we could use to find the numerical value of acceleration g. And that's our answer for part B. Alright, so for part C, to plot the points with the quantities indicated in part B, our y-axis is going to be the length of the pendulum, which is going to be in meters. And our x-axis is going to be the time for one oscillation squared, which is going to be in s squared. And let me go ahead and write that in the data table. T is going to be time for one oscillation. And then t squared is going to be time for one oscillation squared. Okay. So now we go ahead and plot our points. So I'm going to label this as 0.2 right here. This is going to be 0.3. Right here is going to be 0.4. Right here is going to be 0.5, 0.6, and 0.7. Now for the x-axis, this is going to be 0.81. Right here is going to be 1.2. this is going to be 1.613. Right here, it's going to be 2. This is going to be 2.42. And right here is going to be 2.856. Okay, so now for part D, to draw a straight line that best represents the data, we go ahead and plot our points. Oh, for that, actually plot them. Okay, there we go. And then it's going to be right here. This is going to be right here. And then right here. And then right here. And then right here. Alright, so those are our points plotted. Now we go ahead and draw our line for part D. That was part C, which is just going to be a straight line that goes through all these points. Alright, so that's our part D. Thank you. Alright, so in part D, to calculate the gradient of the graph, that's going to be our slope. And our slope is just going to be equal to L over T squared. So L over T squared is also just rise over run. So it's going to be equal to L2 minus L1 over T squared 2 minus T squared 1. And we go ahead and use like the last point and the beginning point. So L2 is just going to be 0.7 minus 0.2 over 2.856 minus 0.81. And if we plug that into our calculator, we're going to get 0.244. So that's going to be our gradient of the graph for part D. Okay, so for part E, to calculate the value of G, we go back to our formula that we found in part B, which is G is equal to parentheses 2 pi squared times L over T squared. So I'm just going to go ahead and rewrite that right over here. And then going back to part C, I'm going to just label it 0, just in case. Alright, now this L over T squared is just going to be our slope, which is going to be y2 minus y1 over x2 minus x1. And our y2 and our y1 can just be 0.7 and 0.2. And our x2 and our x1 can just be 2.856 and 0.81. So I'm going to go ahead and apply that in. So G is going to be equal to parentheses 2 pi squared times 0.7 minus 0.2 over 2.856 minus 0.81. Alright. And if we plug that into our calculator, we get 0.244 times parentheses 2 pi squared. It's going to give us a value of 9.648. So that's going to be our G for part E. G is equal to 9.648 meters per second squared. Alright, so for part F, in order to find the force required to hold the bob in equilibrium, we know that the net force in the x direction is going to be equal to 0. And we also know that the net force in the y direction is going to be equal to 0 as well. So looking at the forces acting on the bob, we know that there's an F of G pointing downwards. The F is going to be pointing this way. And there's also a tension force pointing this way. So we know that the tension force has a y component. And it has an x component, which is dashed. Okay. So in the net force x direction, the net force in the x direction is going to be Tx which is right here, Tx. Forgot to label it. So we have tension force, force of gravity, F, Ty, and Tx. So Tx minus F is equal to 0, which means that Tx is equal to F. Going back to our now force in the y direction. In the y direction is going to be Ty minus F of g. So Ty minus F of g is equal to 0. So Ty is equal to F of g. And now we're looking for F. So going to the y direction, Ty is going to be T cosine theta, because the angle of 12 is given right here, which means that this angle is going to be 12 as well. The angle right here, that is between the Ty and T. So Ty is going to be equal to T cosine theta. So we go ahead and plug that in. T cosine theta is equal to F of g. T cosine of 12, we just plug theta in, is equal to mg. So now we could solve for t. So t is going to be equal to mg over cosine 12. And t of x just breaks down to t sine of 12 equal to f. T of x breaks down to t sine of 12, because again, the angle right here is also going to be 12. So, the angle right here is 12, right? So to find t of x, which is also right here, we could just do sine is equal to opposite over hypotenuse. Hypotenuse is t, and then so it's going to be t sine theta. So that's why it breaks down to t sine theta right here. So now that we have t, we just plug our t in. So it's going to be mg over cosine of 12 times sine of 12 is equal to f. Alright, and now we can plug in our values. So m is just equal to 4. Our g is the experimental g, so 9.648 over cosine 12. And then it's going to be times sine of 12 equal f. So if we plug that into our calculator, which I already did, we're going to get f is equal to 8.203. So f is equal to 8.203 newtons. And since it's magnitude, we don't need direction. And that's our answer for part F. Thank you. Alright, so for part G, to find our net torque, we can set it equal to Fr, F times the perpendicular R. And we can use our F as F of G. And our perpendicular R, we're given L, so we can just find it. And we're given using the angle of 12. So it's going to be right here. This is still going to be 12. So we just find it by doing L sine of theta to find our Lx, which is going to be our R. So we go ahead and plug that in. L sine theta times f of g. F of g just breaks down to mg. Now we're left with L sine theta. Now we can plug in our values. So m is going to be 4. Our g is going to be the experimental g that we found in the previous parts. So it's going to be 9.648. L is going to be 0.5. And then sine. And then theta is going to be 12. So we just go ahead and plug that in. And if we plug that into our calculator, we're given a value of 4.012. So our net torque is going to be equal to 4.012 newtons meters. And since it's magnitude, we don't need direction. Right over here, let me just put the magnitude as well. So that's our answer for part G. Okay, so for part H, to find the tension in the string, we can set up our FC is equal to T minus FG. and FC is also equal to mv squared over r. So we can set these equal to each other. So t minus fg is equal to mv squared over r. And we can add fg to both sides to get t by itself. So t is going to be equal to mv squared over r plus fg. And now fg breaks down to mg. So t is equal to mv squared over r plus mg. Now we have everything except v. So we go ahead and look for that by setting up change in PE is equal to change in KE. Change in PE breaks down to mg times the change in height, which is equal to 1/2 mvf squared minus 1/2 mvi squared. And this just cancels out because vi is just going to be 0. So we're just left with mg times change in height is equal to 1/2 mv squared. So our change in height is going to be equal to L minus the height that it fell, which we could find by doing L cosine theta. So this is the height of the bob when it's at this point. So we can find the change in height by doing L minus L cosine theta. So we go ahead and plug that in. So mg times L minus L cosine theta is equal to 1/2 mv squared. The m's are going to cancel out. So we could just go ahead and times 2 on both sides to get v squared by itself. So we're going to have v squared is equal to 2g times L minus L cosine theta. But L is going to be 0.5. So I'm just going to go ahead and plug that in. So 0.5 minus 0.5 cosine theta. And theta is going to be 12 since it's given right there. So we're left with v squared is equal to 2g times 0.5 minus 0.5 cosine 12. So now we go ahead and plug this back into our equation for t. So t is going to be equal to m times 2g times 0.5 minus 0.5 cosine 12 over r plus mg. And now we have all our values. So t is going to be equal to m times t is going to be equal to 4 times the v squared. And I already found the v squared, which is going to be equal to 0.211. So I'm just going to go ahead and plug that in. So 0.211 over r, which is just going to be 0.5 plus 4 times our experimental g, which is 9.648. So if we go ahead and plug that into our calculator, which I did already as well, we get 40.279 as our tension. So our tension is going to be equal to 40.279 newtons. And again, it's the magnitude, so we don't need a direction. Okay, so in part I, to fact check the student's angular position function, we could begin with our harmonics position function, which is x of t is equal to a cosine theta. And we know that theta is going to be equal to omega times t. So we go ahead and plug that in. So x of t is going to be equal to a cosine omega t. And since the student has a phase shift, we're just going to add a phase shift as well. So now we go ahead and rewrite this as theta of t is equal to theta max cosine omega t plus the phase shift. And so far the student is correct. So now we have to make sure that omega is indeed equal to g over L. So to do that, we can set up our period equation. So period is going to be equal to 2 pi times radical L over g. And we know that omega is going to be equal to 2 pi over t. So if we could get 2 pi over t, we can ensure that omega is equal to g over L. So to do that, we could divide 2 pi on both sides. So t over 2 pi is equal to radical L over g. And now we could just flip both sides to get 2 pi over t is equal to radical g over L. And 2 pi over t, like we said, is omega. So omega is going to be equal to radical g over L, which means that the student's function for the angular position is incorrect, because right here it says that omega is equal to g over L, which is not correct, because we found that omega is equal to radical g over L. So the student's function for angular position is incorrect. Thank you. That's FRQ 3. Thank you.